All right, so in our last video, we went through this series of sample problems where we were solving with the combined gas law, which works great because it allows us to solve for any of those four variables depending on how we change some of the other variables. We could change one thing, we could change three things. It doesn't really matter as long as we know all of the parameters of that combined gas law. The problem is, in the combined gas law, we had to have starting amounts and solving for something after a change. What if we just have a sample of gas and I want to know how many moles are inside of it? I don't want to change anything. I just want to know what's inside this gas. Or maybe I'm going to run a chemical reaction and I'm going to produce a certain amount of gas or moles of gas. And I know the pressure it's going to be under. I know the temperature it's coming off at. So I want to decide how big a container should I be housing this gas in. Okay. Again, no change happens here. So that's a problem with the combined gas law is we need to have a beginning and an end. Okay? So we have another equation that's even more powerful for us to use, which allows us to solve for any of our variables, amount, temperature, pressure, or volume, as long as we know the other parameters. And to do that, we call that the ideal gas law. Okay? We give it this name because we're talking about ideal gases here, and this is kind of like the big one in terms of this unit. This is the most important equation in this entire unit, okay? Now, to get to the ideal gas law, we start with the combined gas law. So if we go back to combined gas law, we knew that the pressure times the volume divided by the number of moles divided by the temperature equals a constant value, okay? There's a constant there, okay? We set that equal to P2, V2, N2, T2 because they're both constant. So this relationship or this ratio is constant with any ending ratio. That's where that law came from. The problem is we don't know that constant, okay? But we do know that if we rearrange this, we can say that the pressure times the volume is proportional to the number of moles that are there times the temperature, okay? So this is a proportionality that comes from the combined gas law. Okay? If we know the pressure and volume, we know that it's proportional to these two things. However, it's not equal to them. Okay? And in math, anytime you know a proportionality or you know things that have a relationship, to make them an equality, all we need to know is is a multiplier. So what multiplier, what special number is going to allow us to make this proportionality an equality? Okay, that special number we call the ideal gas constant, okay, and we label it R. Why R? I have no idea, but that's what we do, okay. R most commonly is seen as 8.314, there is more digits, but we just stop at 4, liters times atmospheres divided by moles times Kelvin. This is not an equation, this is the label, okay. Just like you would say that there is 24 liters of something, or you're at a temperature of 82 kelvins, R's constant has to be labeled to match all the labels in our proportionality. So we have liters for volume, we have atmospheres for pressure, we have moles for temperature, moles for moles, and we have kelvins for temperature. That way, this mathematical constant can cancel out any unit that's inside this math, okay? So don't let this confuse you. This is just a label for our value for R. Often we write it like this, PV equals nRT. It obviously can be rearranged to solve for any of our variables, even moles, okay? Now, a lot of times chemists will give this a nickname PivNert. So if you hear someone say use PivNert, that's what we're talking about. We're saying use this ideal gas law to solve it, okay? It's useful in gases. It's also very useful when you start getting into some energy stuff in the world of physics. All right, so let's take a look at this equation in a little more detail, and we'll watch this little video first. Whoops, I'm backed up.
The ideal gas law relationship between pressure, temperature, volume, and number of atoms can be demonstrated using a piston. As the volume of the cylinder decreases under constant temperature and number of atoms, the pressure increases due to the increased rate of collisions against the wall of the cylinder. We now lock the piston to create a constant volume and number of atoms. Increasing the temperature results in increased kinetic energy for the atoms. The result is an increase in both temperature and pressure. Removing the heat source allows the kinetic energy of the atoms to dissipate to the surroundings, and the system returns to original conditions. With pressure and temperature held constant, additional atoms can be added to the cylinder. This results in an increased volume in the cylinder. If we double the number of atoms, the volume will double under these conditions.
Okay, so that video really was kind of a reiteration of all the things we've already talked about for the combined gas law. You put that together and we get this idea of Pivnert, okay? A couple little details about Pivnert. First of all, the units, okay? Because we're using a gas constant or a mathematical multiplier, we have to make sure our units are very, very specific, okay? So pressure, we often use in atmospheres or kilopascals. Either one's okay, but keep in mind that depending on which pressure you use, you might use a different value for R. In our previous slide, I said we use R as 8.314, but that only holds true when the pressure is in kilopascals, okay? If we want to use pressure in atmospheres, which is the other most common way that we measure pressure, that number would change to 0.0821 liters times atmospheres now, divided by moles times Kelvin, okay? So see how the value changes because the unit changed here, all right? Both are valid numbers, both actually equal each other because of the difference between kilopascals and atmospheres, okay? You actually could convert them into each other if you wanted to. If you happen to have pressure in millimeters of mercury, I would suggest you convert millimeters of mercury to one of these two and then use that as your R value. So I wouldn't suggest finding a new R for millimeters of mercury. That's just my suggestion. Volume is always in liters, okay? So these R values are only valuable in liters, okay? If you change to milliliters, then you have to shift your R value by a factor of 1,000. N is always our number of moles, which is going to become very useful for us because now we have another way to link back to stoichiometry. T is always in kelvins. Again, we have to use that absolute temperature scale, okay, as we go through these. These problems are not inherently challenging in terms of the actual equation because it's 5 variables, but it's very simple math. There's no square roots, there's no functions, there's no sine, there's no log things in here. However, this can be conceptually challenging to make sure that we have everything organized. So let's go through a practice, okay? We have 0.250 grams of CO2 in a 355 milliliter container at 35.0 degrees Celsius. What pressure will the gas exert in the container? Okay, so now to do this problem, before we can get any further, we need to do a little math to even start the problem. Because we're given certain values. So what I'm going to do is what I normally do is I write PV nRT vertically in my work. And the reason why I do that is because I want to track all these variables. I have 0.250 grams of CO2. That's a mass. Mass is not in Pivnert. However, I have knowledge from previous units. I know that if I have 0.250 grams of CO2, I can pretty easily convert that to moles of CO2, okay? I just need to know my molar mass of CO2. So for molar mass of CO2, carbon is 12 and oxygen is 16 times 2, so that's 32 plus 12. So that is 32 as 44.01 grams per mole for CO2, if I did my math right there, okay? I now can solve for moles and use that in my Pivnert equation. I have 355 milliliter container. Again, milliliters is not what I want here. So my volume at 355 milliliters, I'm going to have to slide my decimal to make that 0.355 liters. Okay. I'm at 35 degrees Celsius, which will say, oh great, temperature. But remember, I can't use Celsius, so I have to add 273 to this to be able to solve this also, okay? So 35 plus 273, that would be 308, I believe, kelvins, okay? What pressure will the gas exert on the container? So we're asking for pressure. So my unknown is my pressure, okay? And then, of course, my R. Now, pressure can be either in atmospheres or it can be in kilopascals. Because this doesn't say in kilopascals or atmospheres, we can choose either one we want. Okay, so I can use either R value. I can use 8.314 if I want to go liters, atmospheres, moles, Kelvin, or I can use 0.0821 if I go have it in liters by kilopascals, moles, Kelvin. Either one of those will work, okay? But notice, we've done a lot of work and a lot of math before we even put this into our equation for Pivner. So PV equals nRT. I'm solving for P, so I'm going to rearrange that and say that P is equal to nRT over V. And now I just need to plug my numbers in, okay, and solve this. When it works with the ideal gas law, what you're going to find is that sometimes it takes as much work or even more work to get to use the ideal gas law than it is to actually plug it into the numbers, like you see in this problem, okay? So if we do all that math, here we go. We have 0.250 grams. We have 44.01 grams per mole. That gave me my moles of CO2. I converted my liters over. I converted my temperature over. I rearranged my equation. Plugging in my numbers, my pressure in kilopascals, so I chose to use kilopascals to solve it, these are my moles times 8.314 for my R value for kilopascals. Oh, I did that backwards in my my thing. I apologize. If we go back to our notes, let's fix that because I don't want you to have that wrong. Make sure you change this because this is in kilopascals and this is not kilopascals. I apologize for that. That is atmospheres. I flipped those around. So that is why we check our work as we do that. So we're using kilopascals of 8.314. I'm glad I caught that. Times 308 divided by 0.355. And if we solve that out, solving for it, we get 41.0 kilopascals. If you chose it to do in atmospheres, same math, except for a different R value, we get 0.405 atmospheres. Okay. Notice how these are off by a factor of about 100. Okay. That's because there's about 100 kilopascals in an atmosphere. So that makes sense. All right. So this is how you do these ideal gas law practice problems. Now, there's a lot more to do with ideal gas law because we're going to take the ideal gas law and bring it back into our stoichiometry problems, and we're going to do some more with that as we keep going. Okay. Here's another problem. Okay. What's the mass of sulfur dioxide gas is in a 3.55 liter container at a pressure of 3,500 kilopascals and a temperature of 298 Kelvin. Okay. So in this case, I know my Kelvin's already given to me. I have my pressure. I have my liters. It's asking for the mass of sulfur dioxide gas. So I can't use Pivner to find mass, but I can use it to find moles. And then once I know moles, I can use a little bit of dimensional analysis to find mass. Okay. Again, we use our equation, check our values, use the right R because we are in kilopascals, so we want to be using the right R value. So if we plug everything in, first thing we want to do is look at my equation. So PV equals nRT. I'm going to rearrange it saying I'm solving for our moles now. So PV equals RT. I know my pressure is 3,500 kilopascals. I know my volume is 3.55 liters. I know my temperature is 293 Kelvin. And I know my R value is 8.314. Plugging those things in, I can solve for moles. And when I solve for moles, we have all our values here. Notice how my label, liters is going to cancel, kilopascals is going to cancel, Kelvins are going to cancel. I have moles that does not cancel, so my label ends up being moles. I end up getting 5.10057 moles of sulfur dioxide. Now, I don't want to round this number off yet because it's not my answer, okay? The question said what mass of sulfur dioxide gas is here. So my last step is, if I know the moles of it, I should be able to quickly, using molar mass, solve for the mass of sulfur dioxide gas present, okay? And doing that, we go from moles, find the molar mass of sulfur dioxide, and now we know 327 grams of sulfur dioxide was in that container, okay? So we've done two practices. There's additional practice in your worksheet. I believe it's worksheet number 2 in our files. It gives you more practice. And then we're also going to bring this into even more practice where we're going to start looking at it through the lens of adding in full-blown stoichiometry with the ideal gas law. But we'll do that in a different time. Thank you.